Assalamu alaikum to everyone. So, I don't know, basically, last time we made the couple of videos we made so far that you know about the work done, okay? So, today we will talk about a very new thing in a way that's what we call as the conservative forces, okay? Conservative force, conservative forces, okay? Basically, in order to know what the conservative forces are all about, again, I will use the definition of work done. So I will use here the definition of work done in a more general way that what we have got in the last time. Okay, this is my force, this is my lateral displacement. I will integrate with the limits. So by this way, I'm pretending my definition of the work done again here. So this work done is the more general form of. This equation, what I mean to say, it's more general in a way because it involves what we call the force. It is variable in nature. Okay, this is what we can say the work done under the variable force. So to know the conservative force, I just told you as before, I will use this equation because it will give me the important notion about the conservative forces. How? If I will choose here the limits, what it means then? It means the position of the particle, and this is another position of the particle as well. Okay. So if the force act on a system and the particle that moves, okay, and particle changes its position, let us assume that any arbitrary position of the particle is represented by an x1 and its another position is represented by an x2. So in this way, and the forces are going to be implement. So under this way, and basically, what I'm going to say here, if I will choose any of the path, okay, to move from the position first to the position second, there are the number of physically possible paths by which I can move from this position to this position, okay. So under the effect of the force, okay, if my work done comes out to be same after choosing any other physically possible path between the 2 points, okay, if my work done comes out to be same under the action of force, such a force is basically known as a conservative force. So conservative forces are basically the forces in which the work done between the 2 points after choosing any other physically possible path is same. What I mean to say, if this is my path first, this is my path second, this is my path third, this is my path fourth, this is my path fifth, and so on. So between the 2 points, if I can choose any of the possible path, if it's happened to occur, my work done in each path through each path comes out to be same. If it comes out to be same here, so I can say that my force is conservative. Okay, conservative force is one in which the work done between 2 points through any of the physically possible path is same. Or I can state the same thing in this way, like rather that the work done basically is path independent under the essence of force. These forces are known as the conservative force. Okay. Conservative forces are basically the force in which the work done between the 2 points is path independent. Okay, so this is how we can define the conservative force by using this remarkable definition of the work done and all that. So here we got an idea what these conservative forces are all about. And if I'll just proceed my discussion here in a way that to know more about the conservative forces and all that, see, if I will just use this definition here once more, if I will just rub it for a moment, I will just use my x1 position here and x2 position here. These are the positions of the particle at some point here and at some another point here after the implementation of force. If I will assume that my force is a conservative force here, so if I can follow any of the path, my work done will be same. Okay, it is by the way the property of the conservative force. If it acts on a system and if my work done comes, my work done between 2 points is definitely same. Okay, so I choose here my one of the possible path to go from position first to the position second. I use these kind of subscriptions here. These are what we call as the notions of the, I mean, positions of the particle and all that. Okay. So what I mean to say here further, if I will just use my this path here, so work done across this path, provided that my force is conservative one, so it will be somehow. And if I will just use this path right now, again my force field is conservative here, but I am choosing this path right now. Basically, what it means unto me, simply I am reaching the same point here. Okay. If I return back to my position first after choosing this path or any of the path, doesn't matter. It doesn't matter here, because the forces under which the forces which we are talking about, they are the conservative ones. Okay, under the conservative force field, the positions between the two positions, if we can follow any of the path, my work done is always same. It is, by the way, the definition of conservative force. So here, if I will just look to this kind of, conclusion here, I am getting the sort of closed path here. Okay, so if I will just look for this definition here, I am getting the kind of closed trip here. So if my force is conservative, here is my displacement vector. Under this closed path, my work done will be always 0. The logic is basically simple, because the 2 points are going to be coincide here. My initial and the final points are same. By this way, I can analyze this fact, how exactly this will be happening in principle. Okay. So this is not only the way by which we can understand. There are other ways also, but at the first place we can logically think on it. It is true up to the great approximation and all that. But here simply I'm just looking for the first point. My first point is here. There is no need to open the limits of this integral, because it's a kind of closed curve, so it will take care of everything in this respect. But here if I will just look this very one, instruction here, for instance, my first point is a x1. I use this path here. It doesn't matter when we talk about the conservative force, because my work done will be path independent here. Whatever the physically path I will choose, my work done will come out to be same. It's, by the way, the what we call as a property of the conservative force. If I will choose here for a moment this path to make my analysis simple, so if I will choose this path, I return to the point first by this path. Okay, so I got here the kind of closed loop. The general name of any kind of closed loop, so the general name of any kind of closed curve, it's, by the way, known as loop. Okay, loop is something like the closed curve. Okay, here under this closed curve, and I can say under this loop. So for any kind of closed curve between the two points, provided that my force is conservative, work done will be always 0. Okay, if these are my two particle positions. Okay, and I'm operating this all set under the conservative force, my work done along this path, it will be same as this path. But I am reaching to my same point, so my 2 points are going to be coincide here. By this way, I can feel this kind of conclusion here. It is rightly possible that work done will be 0. But I told you as before, there are another ways as well by which we can explain it. The one of the simplest and the brute way is, what's that? Let me go to discuss that one. Basically, look here. If I will just use my the idea like the conservative force field, there is a displacement, okay, over this closed path, it is going to be 0. Okay, if I will take my left hand side as usual, I will just look for the right hand side. Okay, so my left hand side will be is fc dx. So it will be for path first, what will be the integral? Yes, my integral will be from x1 to x2. My force is conservative here, it's dx. Okay, yes. Now, if I will choose my path second here, what will be the another integral? It will be from x2 to x1, fc dot dx. Okay. Look, if I will just do have one thing, I will change the limits of the second integral in a way, the second integral goes from x2 to x1. For second integral, x2 position is my lower limit and x1 position is higher limit. And we will specifically talking about the second integral now. Now what I can conclude here, if x2 minus x1 will be positive, definitely my x1 minus x2 will be negative. Okay. So for second integral, if I will change the limits of the second integral from x1 to x2, so to make it as usual, I will just opt here the negative sign. This negative sign will take care of everything by this aspect. What's the logic? Logic is simply this. Okay. Now if I will look to this equation right now, so this and this, they are identical to all respects. So I will get here the 0. Okay. By this way, I go at the conclusion like if I will state this thing here, for any kind of closed curve or for any kind of loop between the 2 points, when we operate everything under the conservative force, my work done over the closed circuit will be 0. I give the two logics. What was the first logic? The points are going to be coincide, and the vector integration along the closed curve, it will be 0. That was the logic number first. So, but the more specific logic is this. Okay, I choose this path, my integral will be this. I choose this path, my integral will be this. After doing here some kind of, the usual procedure, and I'm getting here this 0, condition here that predicts, that gives the kind of important conclusion right now. If we are having this integral on the closed path operating all such the conservative force, what is this? This is basically the definition of work done. Okay, my work done will be 0. Okay, this was some more about what happens to our system when we perform something under the conservative force. So when we talk about the example of the conservative force, the finest most example of the conservative force is basically the gravity force. Okay, gravity force, it's a good example of the conservative force, because when we talk about the work done under the gravity force, it gives us the important essence of the quality of the conservative force. Okay, not only the gravity force but the electric force, or in more general way I can say the electromagnetic force. These forces are the conservative forces as well. Okay, in addition, when we talk about the non-conservative forces are such for the work done between the 2 points is path dependent. Means that between 2 points under the essence of the non-conservative force, work done along the different path will be different. Okay, because this value will be always positive by means of the non-conservative force, because they are the type of dissipative force. Dissipative forces are non-conservative forces. Or I can say that an example of the non-conservative force is what we call as a frictional force. It's a very suited example of the non-conservative force. Frictional force. Not only this, the viscous force. Viscous dragging force, it's a type of frictional force, and there is a different physics for, looking the viscous force, but here I'm just presuming that the example of the type of frictional viscous force is basically the type of frictional force. And what's the property of this viscous force? It is basically the velocity dependent force. When the particle moves or object moves in a medium like air, okay, and air offers the kind of resistance for the particle motion, more the velocity of the particle, more resistance will be faced by the particle by means of air. It's a kind of good story, and it's a kind of different story. We need some different physics branch, and we will discuss it at its own place, but it's only here important to mention basically an example of non-conservative force. It's a frictional force, or we can say the viscous force. Not only this, but when we talk about the tension force is a type of force which too an example of non-conservative force. Okay, so it's a moment here to describe something more on the conservative forces. So let me try to analyze that bit also. So when we talk about the work done under the conservative force, we come across the conclusion that basically the work done must be the path independent. Okay, but in spite of this thing, basically when we talk about the work done, it depends upon the position of the particle and the one more position of the particle. This is what we say that these are the endpoints. Between these two endpoints, if we follow any of the path provided that my force is conservative, work done will be always same. Okay. Now here, what's my further point of interest? Basically, if I would look about these two particle positions, okay, my work done will have the strictly dependence on this, because when I look for this integral, there are some limits, lower limit and higher limit. So my work done will under this much of supervision, it will be I mean strictly dependent on the particle positions. Okay. Irrespective of the path independence of this work done under the essence of the conservative force, we got here something very important. Basically, where our the initially particle is, and some later time where my particle is. Between these 2 points, it's obvious that my work done is, I mean, path independent, provide the force is conservative. But what my point of interest is here, work done depends upon the position of the particle, and it depends upon the position of the particle position too here. Okay, so what kind of conclusion we will get here? Basically, my work done will depend upon this position, and it will depend upon this position, because I am just talking about the limits. The physics of these limits gives us a kind of this idea here. Okay, so if I will just analyze this case in a good way here, so I need to introduce one more term here. That's what we call as potential energy. Potential energy is basically defined as the form of energy which is as a result of the position or the configuration of the particle. It is then energy which is due to the position of particle. If my particle position will be here, it will be associated with the potential energy. For a moment, if I will just notify my potential energy, so I define it here. Basically, potential energy, it's a form of energy which is associated with the position, or we can say the more general way, configuration of the particle. These are the two terms, but keeps the meaning identical in a sense. In this respect, so my potential energy is basically dependent on the position of the particle, or I can say under the language of mathematics, potential energy is basically the function of the position. Okay, although it's a scalar quantity basically. Okay, all energies are the scalar parameters, and there's a good quote in physics: work and energies are equivalent quantities. Work and energy are equivalent quantities. Okay, they are not very far from one another, but the ways we define them, they are somehow different, but the actual physics content in both of them represents the same fact. When there is a work, there must be the corresponding energy. Okay, what type of energy? And that's not the bound here, but there is a good quote. I can say the work and energies are equivalent quantities. So if I will just make the connectivity between the work and the potential energy, how I can look this fellow here. I told you as before, when we talk about the potential energy, it depends upon the position. Okay, when it depends upon the position, the particle here will be associated with some potential energy. At some later time, my particle is here under the implementation of the force. It will be here. Okay, so again, it will associated with the form of, it will associated with the amount of potential energy. So if I will look the picture here once more, when work is being done to move the particle from here to there under the essence of the force. Okay, so basically this work done is going to be in against the potential energy. That's the point here basically. So if I need to do the small amount of work done for the displacement of dx, So definitely there must be the change in potential energy that will be represented by differential minus. This is what I mean to say here. If you are getting this point, so my rest of job will be very simple. So basically the amount of work done that I need to do in order to displace the particle by very feeble displacement, that's why I use here. I'm going to say that dW work done, it will be in against the change in potential energy, because when the particle will be here, at some later time it will be here, obviously the particle will associated with the amounts of the, I mean, potential energy contents, okay? So this negative sign here basically gives us an important conclusion that we need to do the work done in against the potential energy. Hope you are getting it. I don't want to consume much more time on it, but anyway, it was a very important thing here to mention. So when we talk about dW work done, it will be yes, provided that my force is conservative, it will be dW is dx, okay, minus du. Look, my conservative force, I can write it as minus du by dx. Okay, okay. So I basically got here something very important. Okay, to make it more general here, if I will use here r, here it will be r, okay? So it will be r. It will be r, okay? So the last expression I got here, it's very important in a sense. So if I will just write it here in a more general way, so then after I will state it. So my work done, it will be yes, it will be minus du by dr vector, or I can say under the language of physics, we write it more often like this. This is very important equation. Okay, sorry, it's my conservative force here. So the kind of conclusion I got, whenever I talk about the conservative force, we can write it as, this is what we read in physics, the gradient, okay? So the conservative forces can be written as a negative gradient of the potential energy. Negative gradient of the potential energy. Negative gradient of the potential energy, okay? So this is the form of, equation I got here. So this is the mode of defining the conservative forces in terms of the potential energies. More oftenly, when we talk about the non-conservative force, there is not such type of relation which is possible here, okay? So because non-conservative forces are the dissipative forces, the work done along the different paths will be different, okay? Not only that, the work done, the work done integral, that's f ds, it will be always positive. It will be always positive, okay? So that's why we are not able to write down non-conservative forces as a negative gradient of the potential energy. So the kind of important conclusion we have here so far, the conservative forces can be written as a negative gradient of the potential energy, okay? So for more, for advanced students, if I will just write the structure of this gradient here, so what it will be is, it's basically read as a negative gradient of potential energy, okay? This is what it means, okay? Yes. So I told you as before, I will just go for to write the structure of this gradient here. So in a more general way, we write it as like this. Partial by partial x, I will shortly come on to this, what it means, and I plus partial by partial y of j plus partial by partial z of k. This is basically the partial derivative, and this is an ordinary derivative. What's the difference between the partial and ordinary derivative? How we can, make the kind of distinction between the two types of derivative. For instance, if I have the kind of function that involves the more number of variables, okay? Now, under the treatment of the partial derivative, it means that if we are differentiating it with respect to x, okay, means that under the treatment of the partial derivative, I need to take the rest of variables as constant, okay? And this is, only the difference between this ordinary and the partial derivative. If my function involves more number of variables under the partial derivative operation, I need to take the rest of variables, constant under this treatment. Okay, so this is how the partial derivative is different from, I mean to say, an ordinary one. Okay, this is I mean the way how we can express here everything by means of the partial derivatives and all that. Not only this, sometimes if it will be given in a problem, like if there is a force expression and we need to find or we need to figure it out whether the force equation represents a non-conservative or conservative force. For that, what we need to do, basically I will just find the very important condition. That condition is basically, it will be the come out of this equation. Okay, how we can just look for the conditions which will be, I mean, which will give us the kind of notion that if sometimes in a problem the force equation will be given and we need to find whether the given force equation will be conservative or not. For that, I have to look for the kind of conditions here. What are the conditions? These conditions will be I mean created from this equation. Okay, so for that, let me start here. So if these conservative force, I can write my conservative force as f of x I plus f of y j plus f of z k. Means here I write simply my conservative force in terms of its components. Okay, nothing here to worry so far. If I will put this type of way in here, so what I will get here is simply my f of x will be minus partial u by partial x. Okay, number one. Number second component will be my partial u by partial y, and my third component f of z will be minus partial u by partial z. These are the, I mean, how we can write the components of force in terms of the potential energy derivatives and all that. So if I will just differentiate the above equation partially with respect to y, I will get here partial x by partial y. It will be minus partial square u by partial y partial x. Okay, I will number it first. Here what I will get is, I will get, if I will differentiate it with respect to x, partial fy by partial x, it will be minus partial square u partial x partial y. Now I will just number this equation second. Look, if I will look equation first and equation second, their right hand sides are equal. Means in that their left hand sides must be also equal. Means in that by partial f by partial fx by partial y, it should be partial fy by partial x. This is a condition, one condition. Okay, and I can find another conditions from this equation. I don't need to worry here the kind of mathematics here, because it's a kind of symmetrical conclusions I will get from this equation. But this is a kind of, equation, and it's a condition for the force equation. It should, if the force equation consists of the two components f and x and y, then this condition should be satisfied by means of the partial derivatives. Then and only then our given force equation will be conservative. Okay, otherwise not. So this is the one kind of condition that a force equation should satisfy by means of these partial derivatives and all that. So I can find them some analogous condition by using this equation. Okay, without any so I can use this equation here by find some analogous condition. If I write my partial f, so when there is x here, there is y. Okay, when there is y here, there is x. Let us assume that if there is z here and there is x, there must be f of x here and f of z. Okay, this is one way how we can find some analogous condition. Not only this, this is one more condition, and that is something which the conservative force represents. And there is one more analogous condition I can find here. If I will use here y, here I will use z. So here I can use z, I can use here y. Okay, this is one more condition. Is there, do you feel there is any kind of combination that's spanning here? If I will use here z, y, why is that? It means everything, all is going to come here. Okay, these are the conditions which are basically the representatives of the conservative forces. Okay, so if I will use here the force equation example, and which we need to find whether the given example of given the expression for force is conservative or not. For that, it should satisfy this kind of condition. Okay, so here if I will just mention an example of the force equation. Like suppose in the previous discussion I use somewhere this force equation like this: x square y square I plus x square y square j. Okay, I should here figure out whether the given force equation is conservative or not. For that I should must look for the condition f of x by partial y. It should be partial f of y by partial x. Okay, I don't need to look for another condition, is because my force equation, it only involves the two components. My fx will be here, yes, x square y square, and my fy will be here, yes, again x square y square. So if I will just differentiate this equation partially with respect to y, so partial f by partial y, it will be, yes, it will be putting this x square constant, we can find here 2y. Okay, not only this, if I will find here one more condition, I can differentiate partially with respect to x, so I will get here, yes, 2x y square. Okay, so this condition tells me that this and this, they must be equal. This is only possible when the right hand sides are equal, but the right hand sides doesn't seem here equal, means that 2yx square is not equal to x y square. Okay, so basically the given force equation is non-conservative, okay. So this was some special information about the conservative forces, how we can look for the check, which gives an important idea the given force will be conservative and not. So the given force expression I mentioned here, it's not basically conservative because it does not satisfy this condition. It does not satisfy this condition. So it does not satisfy this condition. Why so? Because we find the partial derivatives. So this condition is not going to be satisfied. We can safely say here, our force expression, it's not conservative. So this was some key idea about the conservative force. Okay, so this was all about this. Thank you.